A generator can have enough watts to run your central air conditioner and still fail the instant the compressor tries to start. That sounds impossible until you separate two jobs. Running an air conditioner is one job. Getting a stopped compressor moving is another. The second job can demand a brutal split-second burst of current. If the generator cannot deliver that burst while holding voltage and frequency together, the lights sag, the engine groans, a breaker trips, or the compressor simply does not start. This is why a homeowner can add every normal load correctly, buy a generator with a reassuring 5-digit number on the box, and still end up sweating in a dark house. The mistake is not always buying too few running watts. Sometimes it is buying the wrong kind of electrical headroom. By the end, you will know where to find the number that matters on your own air conditioner, why a 50 amps outlet does not automatically mean 12,000 watts of usable power, what a soft starter can and cannot fix, and how 5 current generators fit very different central air plans. Start with the easiest trap, voltage. Most residential central air condensers are 208 or 230 volts or 240 volts equipment. A 120 volts generator cannot power that load through a normal code-compliant home connection, no matter how impressive its starting watt number looks. Champion's Model 201534 is a perfect example. The product is rated at 5,500 starting watts and 4,000 running watts on gasoline. Those numbers sound large beside a refrigerator or a window air conditioner, but the generator is 120 volts only. It can be a useful small load machine. It is not a central air solution for a typical 240 volts condenser. That distinction should happen before any wattage arithmetic. First ask whether the generator produces the voltage your equipment needs. Then ask whether the outlet, transfer equipment, wiring, and generator rating can deliver the required current. Only then do the headline watts become useful. Now look at the air conditioner itself. A current Goodman ALZS5B specification gives us a clean real-world example. The 36,000 BTU per hour, or 3-ton, ALZS5BA3610A model lists a compressor-rated load current of 16.4 amps and a locked rotor current of 88 amps. The condenser fan adds another 1 amp of full load current. Those two current numbers describe different conditions. RLA, or rated load amps, is a reference used around normal compressor operation. LRA, or locked rotor amps, is the current associated with a motor that has not yet begun turning. When a compressor starts, it has no spinning momentum and no helpful back electromotive force. For a brief moment, the electrical system sees something much closer to that locked condition than to a settled running load. This does not mean the air conditioner consumes exactly 88 amps for seconds at a time. It does not mean you can multiply 88.0 by 230 and call the answer generator watts. Motor starting is reactive. The power factor changes, and the current falls as the compressor accelerates. But the scale is still useful. At 230 volts, 16.4 amps is roughly 3,772 volt-amps before adding the outdoor fan and the indoor blower. At the same voltage, 88 amps represents a momentary apparent burden above 20,000 volt-amps. That is not a billable running watt figure. It is a warning that normal operating demand and starting demand can live in completely different neighborhoods. Generic wattage charts smooth that mess into an estimate. Champion's current guide places a typical 3-ton central air conditioner around 3,000, 3,500 running watts and 5,000, 6,000 starting watts. That is useful for early planning. It is not permission to ignore your own nameplate. The chart cannot know your compressor design, indoor blower, outdoor temperature, refrigerant pressure, wire length, elevation, other house loads, or whether the unit is a conventional single-stage compressor or a variable speed system. The actual equipment label and manufacturer data always beat a generic chart. There is another common arithmetic mistake. People add the running watts for the refrigerator, freezer, lights, furnace controls, well pump, and air conditioner. Then they add every starting watt number on the page. That can oversize a system unnecessarily because those motors do not usually start at the same exact instant. Champion's operating guidance uses a more practical method. Add the running demand of everything that may operate together. Then add the highest single starting requirement among those loads. That gives a planning target for the worst normal start while the other loads are already running, but central air exposes the weakness in that shortcut. If the compressor's actual start is harsher than the chart estimate, or the well pump happens to start during the same second, the real event can exceed the plan. Load management is not just a spreadsheet, it is deciding what will be allowed to run together. Imagine a house carrying 700 W of refrigerator and freezer load, 500 W of lights and electronics, an 800 W indoor blower, and a central air system settling near 3,500 watts. The running total is about 5,500 watts. On paper, a generator rated for 7,250 running watts looks comfortable. Now let the compressor start. If the air conditioner needs a 6,000 watt starting allowance, the generator must temporarily support that start on top of the other running loads. The planning demand moves toward 8,000 watts. If a well pump or microwave joins the event, the margin disappears. Those are illustrative numbers, not a promise about your home. Your refrigerator may draw less. Your blower may draw more. Your compressor could start much harder. The point is that the quiet loads already consuming power do not vanish when the largest motor starts. This brings us to generator labels. Starting watts describe short duration capability. Running watts describe continuous capability. Neither number tells you everything about voltage recovery, alternator response, engine response, or how long the advertised surge is available. The Champion Model 201176 lists 9,000 starting watts and 7,250 running watts on gasoline. It produces 120 or 240 volts and includes both 30 amps and 50 amps receptacles. That makes it electrically relevant to a managed home backup plan in a way the 120 volts Champion Model 201534 is not. But relevance is not a guarantee. A 7,250 watts running budget can disappear quickly when central air shares the generator with a blower, refrigeration, pumps, and kitchen loads. The 9,000 watt starting number may cover a modest compressor start under controlled conditions. It may not cover a harder starting unit with the rest of the house still awake. The Cummins Onan P11000 ITF moves up a class. On gasoline, it is rated for 11,000 peak watts and 9,000 running watts. It provides 120 or 240 volts, 30 amps and 50 amps connections, and inverter output specified below 3% THD. That extra running room makes simultaneous load management easier. It does not erase the compressor nameplate. A difficult conventional compressor can still present a starting event that overwhelms a portable generator, especially after fuel derating, elevation, or other active loads reduce the margin. The DuroMax XP13000 HXT is a high-output conventional example at 13,000 peak and 10,500 running watts on gasoline. The Westinghouse WGen 11500 TFC goes further at 14,500 peak and 11,500 running watts on gasoline. Both provide 120 or 240 volts and 50 amps class connections. These larger machines improve the odds because they carry more continuous load and more stated surge. They also show why the outlet itself is not the answer. A 50 amps, 240 volts connector has a theoretical 12,000 volt amps connection capacity. The generator behind it may be rated below that continuously. The receptacle is a connection standard, not a promise that the engine and alternator can deliver 12,000 watts forever. The same warning applies in reverse. A 30 amps, 240 volts connection represents 7,200 volt amps at the connector. A generator with a larger total rating cannot push unlimited power through that one outlet. The lowest applicable limit in the chain still matters. Generator rating, receptacle, breaker, cable, inlet, transfer equipment, and the connected circuit. This is why central air backup belongs on a real electrical plan. A listed transfer switch or correctly configured interlock must isolate the home from utility power. Conductors and overcurrent protection must match the installation. The air conditioner cannot be treated like a toaster on an extension cord, and a portable generator must never be backfed into a receptacle. There is a tool that can materially change the starting problem: an electronic soft starter. A soft starter does not make the air conditioner free to run. It changes how the compressor accelerates, spreading the start over a controlled ramp and reducing the peak current demanded from the generator. MicroAir's Easy Start Flex documentation says the device can reduce peak starting current by up to 75%. The important words are "up to." That is a manufacturer maximum claim, not a guaranteed reduction for every compressor, generator, and installation. MicroAir's own generator sizing guide keeps the conditions attached. It tells buyers to size from continuous generator capacity, account for other significant loads, use actual compressor information, and allow for conditions such as elevation. Its example does not say that a soft starter turns any small generator into a whole home generator. The device also has application limits. Easy Start Flex is specified for 100 to 250 volts AC, single phase, 50 or 60 Hz applications within its supported compressor range. Compatibility, installation, learning starts, existing HVAC controls, warranty questions, and local electrical requirements still have to be checked for the exact system. A soft starter is also not the same thing as a hard start kit. A hard start kit typically adds start capacitance to help a compressor accelerate. A soft starter actively manages the start sequence to reduce peak current. They solve related problems in different ways. Installing one should not be improvised from a generic internet diagram. The work involves hazardous voltage and the HVAC manufacturer's requirements. The best way to understand the benefit is to return to the Goodman example. Its 88 amps LRA is not a measured easy start result. If a compatible soft starter materially reduces the actual peak inrush, the generator faces a much smaller transient. But the compressor still has its running load, the indoor blower still draws power, and every other active circuit still counts. So a soft starter can move a project from obviously unrealistic to worth measuring and engineering. It does not move it straight to guaranteed. The proof is a compatible installation and a successful start, while the generator carries the real loads that matter. Fuel choice matters too. Video 2 showed that the same tri-fuel generator can provide less output on propane and still less on natural gas. If you intend to run natural gas, every central air calculation must use the natural gas running and starting columns, not the gasoline headline. For example, the Westinghouse WGen 11500 TFC drops from 11,500 running watts on gasoline to 9,500 running watts on natural gas. The DuroMax XP 13000 HXT drops from 10,500 to 8,500 running watts. A central air plan that barely works on gasoline can lose its margin when the fuel changes. Elevation and heat can also work against you. Engines produce less power as air density falls, and the generator manufacturer may specify a derating procedure. Air conditioners are often asked to start during the hottest part of an outage, when system pressures and household cooling demand are high. Planning at the edge leaves no room for the real day to be worse than the worksheet. Variable speed air conditioners can behave differently from conventional single-stage compressors. Their electronics may ramp the compressor rather than applying a traditional across-the-line start. That can reduce the classic inrush problem, but it introduces model-specific power electronics requirements. Do not assume inverter air conditioner means works with any inverter generator. Check the exact HVAC documentation and the generator plan. It also helps to recognize what a failed start looks like. The compressor may hum without accelerating. The generator may dip sharply, then recover when an overload opens. A breaker may trip. Some modern HVAC controls may stop the attempt on low voltage and wait before trying again. Repeatedly forcing another start is not a sizing test. It can heat motor windings, stress contactors, and turn a planning problem into an equipment problem. The correct response is to stop and find the limit. Measure the generator voltage and frequency during the event with suitable equipment. Confirm which loads were already active. Check the generator's overload indication and the air conditioner's fault history. A qualified technician can measure actual inrush and compare it with the nameplate and manufacturer requirements. That information is much more useful than a comment saying a certain generator runs a 3-ton unit, because two systems with the same nominal tonnage may not start alike. Do not confuse breaker size with normal consumption either. A condenser protected by a 40A breaker does not necessarily draw 40A continuously. The breaker and maximum overcurrent value protect the circuit under defined conditions. Minimum circuit ampacity helps size conductors. RLA and fan current describe other parts of the equipment rating. LRA describes the compressor's locked condition. Each number has a job. None should be substituted for all the others. This is where a clamp meter measurement can be valuable, but it belongs in qualified hands. The condenser cabinet contains hazardous voltage even after power is switched off, and capacitors may retain charge. Generator Truth is not asking you to open the unit. We are asking you to collect the model and nameplate information, then get competent measurements when the design is close enough that the real start matters. The practical buying process is simple even though the engineering is not. First, identify the exact outdoor unit model and photograph its nameplate. Record voltage, phase, RLA, LRA, minimum circuit ampacity, and maximum overcurrent protection. If the label is unreadable, use the exact manufacturer model literature, not a chart for a similar tonnage. Second, list the loads that truly need to run with cooling. Include the indoor blower, refrigeration, pumps, lights, communications, and any fuel system or control loads. Separate continuous demand from motor start demand. Third, choose the actual generator fuel. Use that fuel's running and starting ratings. Apply the manufacturer's altitude or temperature derating when required. Verify 240 volts output and the limits of the intended receptacle and connection equipment. Fourth, decide how loads will be managed. A homeowner may shut off an electric water heater, range, dryer, or pool equipment before allowing central air to start. Automatic load management equipment may be appropriate in a professionally designed standby system. The objective is not to power every breaker just because it exists. Fifth, evaluate whether a compatible soft starter is appropriate. Treat its reduction as measured system behavior, not a universal percentage. Have qualified people handle HVAC and panel work, especially when equipment warranty or code compliance is involved. Finally, test the finished system under controlled conditions before the emergency. Confirm voltage remains acceptable. The compressor starts cleanly. The generator recovers. Protective devices do not trip, and the planned simultaneous loads behave as expected. A paper calculation is the beginning of verification, not the end. Here is the honest product takeaway. The Champion Model 201534 is a poor fit for typical central air because it is 120 volts only, regardless of its 5,500 watts starting headline. The Champion Model 201176 is a plausible managed load starting point for smaller or softened 240 volt systems, but its 7,250 watts running budget demands discipline. The Cummins P11000 ITF offers more continuous room and inverter power quality at 9,000 running watts, but it still needs the exact compressor and fuel plan. The DuroMax XP13000 HXT and Westinghouse WGen 11500 TFC provide stronger gasoline headroom for larger managed load plans. On natural gas, both lose 2,000 running watts, so the central air margin must be recalculated. None of those conclusions is a universal recommendation. The generator is only one half of the match. The air conditioner, connection, fuel, elevation, and other loads are the other half, and that is the buying trap. Enough watts is not one number. Central air needs the right voltage, enough continuous capacity, enough transient response, a compatible connection, and a starting plan grounded in the actual compressor. Read the air conditioner nameplate before the generator brochure. Size from the fuel you will really use. Control the loads that can overlap. If a soft starter is part of the plan, verify the result instead of assuming it. That is how a generator becomes a working backup system instead of a very expensive engine that cannot keep the house cool.